All right, this is one of the progress check free response questions. Look like a good one to go over. It is line 30 and 31 on the spreadsheet that I gave you for this year. And this is a long free response. And it looked like it had a decent amount of stuff in it, including some kind of lab design stuff as well, I believe. So let's take a look. So we have a solid block X of mass mx may be placed at different locations along this curved ramp. At the bottom of the ramp is a solid block Y of mass my that is at rest on the horizontal surface. Figure 1 shows both blocks before block X is released. A group of students must graphically determine the relationship between the release height of block X and the speed at which the two block system travels after the blocks collide and stick together. So this is an inelastic situation. Figure 2 shows the blocks after the collision. Frictional forces between block X and the ramp and between both blocks and the horizontal surface are considered negligible. So no friction at this point. All right, so the relationship is between the height and the speed here. But there's a collision involved as well. So I don't know exactly how I'm going to do this yet, but I see potential energy here. I see kinetic energy here, but there's momentum in between. So we'll have to sort that out as we go. We'll keep this drawing handy. So our task is A, state the basic physics principles, laws, or equations that students could use to graphically determine the relationship between the release height of the block X and the speed at which the two block system travels after the blocks collide and stick together. So, all right. So basically, what I mentioned a moment ago is what they're asking you to do. So, for example, H here, well, if I'm going to use H, then it's got to be the potential energy at the start. So I'm just going to jot down, well, I know the U at the top is mxgh. And H is important because that is going to be, let's see, they want to know so I think this is going to be like our X, the release height, and the final velocity after they collide is going to be like our Y. But for now, I know this is important. And I also know that that will equal the kinetic energy of block X just before it collides here. Because there's no friction, so it's going to, all of this potential energy is going to turn into kinetic. So that will turn into 1/2 mx. Let's see. Now, what do we want to call this? We're going to call this v before. So velocity of x before the collision. The subscripts become important here because we have to make sure we know what we're talking about. This is the velocity of the x block before it actually collides. Squared, of course. All right, so I know I can get from h to the kinetic energy here to here. Now I have the collision. Well, the collision is the realm of momentum. So I have initial momentum has to equal final momentum. All right. Initial momentum would be in the form of block X because this one's stationary. So it would be mx times vxb period. There's no square there, right? So it would be those two times each other. But this, if I had to, I could describe in terms of h. See the connection here? So I have this. I need h, but there's a connection. There's an equation involving the two of them. But we'll come back to that. That's the initial momentum. The final momentum, they stick together. So it's just mx plus my, the two of them together, times, what are they calling that velocity? This is the velocity they really want. And the speed, so we'll just call that v final. Boom, like so. So we have, here's the set of equations. I think this is all they want here. They just state the basic physical principles, laws, or equations. So you could state potential energy at top, all right, equals kinetic energy at bottom, And then from that kinetic energy, I can get the velocity. There's a velocity involved. And then I can use conservation of momentum to find the final velocity, set up an equation for the final velocity. This is roughly what they want. Now they want derive an equation that relates the initial release height, they call it hx, okay, of block X, and the speed, they call it vs. I can't even tell what that says. And I'm right here. We're going to use this to see if I can. And it looks like an S. All right. So VS. So I guess instead of V final, so all of a sudden they tell me what I should be calling these things. That's kind of annoying. So this, what I call V final, they would like me to call VS. That's fine. That's fine. We can do that. And what I just called H, which is what they want me to call 8 big H X. Fine. Fine. But basically, they want that in terms of, they want to relate this and this. You can use this, this, and G. So what we can't use is this in-between velocity, but we're okay there. So what I'm suggesting that we're going to do is solve over here, solve for this X velocity, the X's velocity just before the collision, because that expression will have an H in it and a bunch of M's. Plug that in here, and all of a sudden the only things you'll have are masses, H, and the velocity we're looking for. So we need to solve this first, and we need to solve it for this, not H, because we want to replace, substitute it in here. So let's try that. So we're going to take mx times g times this initial height equals 1/2 mx velocity of x before the collision squared. So this is kind of like an in-between variable. We're actually going to eliminate it. The good news is the m's go away. So if I'm solving for this, I'm going to multiply by 2. So I have 2ghx equals v velocity of x before the collision squared. I got to take the square root. So that velocity of x before the collision is the square root of 2ghx. That is what I'm going to plug in here. So I'm going to have my initial momentum is mx times the velocity just before the collision, which I can now describe in terms of the h, square root 2ghx, equals the final momentum, which is mx plus my, times what they call vs. Now, if I'm reading them correctly, the independent variable is this height, and the dependent is the speed. So basically, we're solving for this speed. This is our y. This is our x. No big deal. So I'm going to do a couple steps here. Well, let's just do one step at a time. mx plus my. Now just Alright, just switch sides. Now I'm going to divide by mx plus my. And that speed at the bottom is going to be mx times the square root of 2gh sub x over the sum of the masses. Alright, so there's an expression that involves h, where vs is a function of h. Constants and masses are the only other things allowed, and that's what we have. Just mx, my, and fundamental constants. Well, 2 counts as that, I suppose. All right. So let's summarize. You go back, let's recap what the hell happened there. So from the picture, what you should see is that you have gravitational potential energy here. And that turns into kinetic energy here. And they are the same because there's no friction on the ramp. Then you have a collision. And then you have this. And so the potential energy here equals the kinetic energy just before. The velocity involved in that kinetic energy is the velocity of this larger block just before the collision. So there's the link between the energy and the momentum part of it. And so I'm using the energy part of it to get the velocity just before the collision in terms of h, so that I can substitute it in, and then I can use h comes along and I lose this in between velocity that I don't really need. And then the algebra. Interesting, if they may ask us later this has a square root in it. I would not be surprised if I was going to linearize this, which means I would probably plot something like the square root of hz with respect, that would be like my x, and my y would be vs, and the slope would be all this other garbage that's in there. So I can see that maybe being something, but I don't know. I haven't looked at the rest of the problem. Let's see. Blank page. All right. Design an experimental procedure the students could use to graphically determine the relationship between the release height of the block and the speed at which the two blocks travel afterwards. All right, on the table below, list the quantities associated, symbols that you would measure in your experiment, and the equipment used to measure them. Also list the equipment that would be used to measure each quantity. You know what they said in a quick experiment? And the equipment used to measure them. Also list the equipment that you would use to measure each quantity. Anyway, you do not need to fill out every row. If you need extra rows, add them in. All right, well, let's take a look. Certainly we're going to need to measure the initial height. And that would be like, say, meter stick or something, right? Or tape measure. So mx, symbol for the quantity. Maybe that is mx. All right, so I guess they want us to say the quantity. All right, that's a problem. We can use words. Initial. Actually, that's not mx anyway. Initial height of block X. So that would be hx, my apologies. And that would be a tape measure or meter stick, either one. Now, we need to measure the masses of everything. So, mass of X would be mx and would be, say, a digital balance or a force probe, scale, something like that. Digital balance. Mass of Y, my, same thing. And then the last thing I guess we're going to need is the speed afterwards. So we're going to have to put when they come off of that ramp, here's the quick way to measure speed, is just put a force probe sitting right here, not a force probe, take that back, a motion detector right here that will read the speed as it comes towards it. That's all you got to do. So motion detector is your friend. And this is the modern ages, so you're allowed to say that your school's fancy and has one. And I have shown them to you. Don't tell me I haven't. So Vs, or the velocity after collision, not a lot of space here for you to write. Call it Vs, and that's going to be motion detector or sensor. And that should be all we need. We get Vs from this, the masses that we need, because remember, if we did a good job, we know all the quantities that we need. Vs I get from the motion detector, G is just a constant, H I can get from a tape measure, and these I can get from digital balances. Digital balance, I can use it once, or multiple times I should say. Okay. Now I'm just looking to see what... Now we describe the procedure. Okay. Because they kind of say they describe the procedure here, but then they just want you to do the table. So, all right. Describe the overall procedure to be used, referring to the table, provide enough details so that another student can replicate the experiment, including any steps necessary to reduce experimental uncertainty. All that means is run multiple trials, folks. Just, if you don't even know how to fill this out, when you see that phrase, just say, I would run multiple trials, and you're going to get that point. All right, so describe the. So I'm gonna go with this. Depends on how much detail you want to get into in the time you have, right? So, and I like using bullet points. I hope they're okay with it. Place, well, first, measure MX and MY using digital balance. Because that's going to stay the same the whole time. Okay. Next. Place MY at the bottom of the ramp. On flat surface, just to make sure everybody. Hold MX on ramp and measure HX using tape measure. And you might want to say something about start data collection on motion sensor. And then release block MX. Use data from motion detector to determine VS. And I would put a picture in. They gave us a picture, but just to make sure. So show that this is the distance you're going to measure. HX. Sorry. Show that you're going to place the block here. This is block Y. Show that the motion sensor or motion detector is going to be here somewhere. All right, and that should be enough. There, yep, you show where the motion detector is. That's going to measure the speed of them after the collision. This is HX, that's what you're measuring with a tape measure. If you want to draw your little scale over to the side here, that's fine, but I'm not really sure that you need to do that. This should be pretty clear. All right, it's not bad. Oh, and then repeat, almost forgot, at least 5 to 10 times at different heights. So not always at the same HX here. Make it higher sometimes, lower sometimes. Okay? So that would be your experimental uncertainty bit. Cool? All right. Students repeat the experiment, but replace block. All right, but replace block X and Y and blocks Y with block W and block Z. Sounds like a Dr. Seuss book, as shown in Figure 3. Block W and block Z have identical mass, M, mass M. When the experiment is conducted, the students observe that the blocks do not stick together, as shown in Figure 4. Now they bounce off each other. Okay. The students predict that the speed of block Z after the collision, by assuming the collision is perfectly elastic. We should know, by the way, that it's rarely the case that the collisions are perfectly elastic. Then they collect data about the actual speeds of the blocks, both immediately before and after the collision, as shown in the table. So here somehow they got the speed of block W and the block Z after the collision. Why does the predicted speed of block Z after the collision not agree with the actual speed of block Z? So they're saying predicted speed is this, actual speed is less. Predicted speed is this, actual speed is less. So it is because the collision is not completely elastic. It is somewhat inelastic, which is really all you have to say. I'm trying to decide what else do I need to. Yeah, I can't. The only thing that's a little strange is that the actual speed. Well, no, hold on. Oh, this is the speed of block W. So here it's almost stopped backward. This, I would say, it averages that it does stop. Like, it's really close to stopped. But here we definitely see for Z, for block Z, it's not moving as fast as it was. And it's because that the collision is not perfectly elastic. That's all I would say. Question is that all they want to know? We'll have to look at the answers at some point. All right. I don't know if I have those answers really handy here or not. Let me see. I might. Yeah, there we go. So let's see what they want us to say. Example, so there's 2 points for that last part. Example response. The collision between block wand, I think it's just W, and block Z is not perfectly elastic, even though the two blocks do not remain stuck together. During the collision, the two blocks may have momentarily stuck together, or one of the blocks have slightly caused a temporary deformation. Okay. So 1 point is earned for indicating that the collision is not perfectly elastic. So we would have gotten that. All right, why? Okay, well, yeah, so deformation, loss of friction due to the bending of the wood. They said another thing would be like they do slightly stick together and then come apart, something like that. We'd have gotten this point. I'd have gotten this point. I guess I could have gotten this one saying that somehow the wood gives a little bit and there's some frictional losses in there. All right, not bad. All right, I think everything else I pretty gotten full points on. I don't want to take forever on the video for you. Thanks for watching.